Now, we are coming towards work done by variable force. That is, force is variable, possibly the work done is not. So, we find if the force applying on a body is changing in its direction or magnitude or both, then force is said to be variable. So, either if the direction changes or the magnitude changes, then force is supposed to be variable. Now, we assume a force causes displacement in the body from P1 to P2. This will be clear in the figure, which is mentioned further. To calculate the work done by force, the path from P1 to P2, when we speak P1 to P2, we have to just see the figure. It can be divided into infinitesimally elements. Each element is so small that during displacement of the body through it, the force is supposed to be constant. If dr is the small displacement of body and F is the force applied to the body, the work done by force is the dot product of F and dr. So dW is equal to F dr. Now, in order to find the total work done in displacing the body from P1 to P2, we have to integrate dW. So, what we have done, we have integrated dW, and the limits of integration are from P1 to P2, that is lower to higher, and the product is F dr. So, with respect to dr, F will be constant. So, we integrate this function as it is shown that R1 and R2 are the positions of vectors of P1 and P2 respectively. The work done will be. So, we have calculated integration of dW, that will be W. That is integration from R1 to R2 from lower to higher limit Fd dr. And now F is taken out as a constant before the integration sign, and then we will integrate 1 dr, which is found to be R, and then we put the limits R1 and R2, and the final function will become F into R2 minus R1. So after integrating this function, the total work done will be F into R2 minus R1. Now, when we consider a block attached to a spring, the force on the block is K times the elongation of spring, and K is supposed to be the spring constant. When we say spring constant, it is basically force per unit displacement, and its unit is Newton per meter. In order to find its dimension, we put the dimension of force and we put the dimension of displacement. So K is a spring constant, that is force per unit displacement. As the elongation changes with motion of the block, therefore the force is variable. This is an example of the work done by variable force. Now we have a question. A position dependent force, that is F is equal to 7 minus 2x plus 3x square, acts on a small body and the mass of the body is 2 kilograms and displaces it from x0 to x5. The work done in joules will be how much? In order to find the work done, we have to integrate a function. So by integrating, the limits will be from minimum 0 to maximum 5. So here work done is integration x1 to x2 f dx. Now f is constant, integration 1 dx will be x, and the limits will be put from x1 to x2, that is from 0 to 5. After putting these definite values, it's a case of definite integral. We put the values and then x will be taken from 0 to 5. So we will put these values of x and we get 135 joules. Now next question is, a uniform chain of mass m and length L is lying on the frictionless table in such a way that its 1/3 part is hanging vertically down. So out of L, 1/3 part is hanging. So remaining part on the table will be L minus L over 3. So the work done in pulling the chain up to the table is, work done is obviously the dot product of force and displacement. So that fact is to be applied in this question. So if length x of the chain is pulled up on the table, then the length of the hanging part, as I have explained, that will be L over 3 minus x, and the weight will be, that is weight is force. So it will be m over L into L by 3 minus x. into G. So total mass will be m over L into L by 3 minus x, and G is acceleration due to gravity. If we take the product, it will become weight. If it is pulled up further by distance dx, the work done in pulling up will be calculated by integration. So we have integrated the function m over L into L over 3 minus x into G with respect to dx. The integration appears in the form of mgl over 18. mgl over 18. Now, the calculations of work done from the force displacement graph. Now we have to come towards the graph, the displacement on one axis and the force on another axis. We have to make calculation graphically for the work done. So, here the statement is given and the graph will be in this part shown to us. Suppose a body whose initial position is R1, indicated in figure at M, is acted upon by variable force F, and consequently the body acquires its final position R2. So when we apply the force, the final position from R1 to R2 acquire its final position. From position R to R plus dr. Dr is a small element for small displacement dr. The work done will be Fdr, whose value will be the area of the shaded strip of width dr. So shaded region area has to be calculated in order to find the work done. So the work done on the body in displacing it from position R1 to R2, what we do is we take small work done and we take the summation. So sigma stands for summation of dw, that is the small work done, and then we will take the summation, the limits from R1 to R2. So in the another part we have written summation R1 to R2, the product F dr, and that is equal to area of P1, P2 and M as it is clear from the figure. The area between the graph, between the force and the displacement axis is equal to the work done. Now, important note is to calculate the work done by graphical method. For the sake of simplicity, here we have assumed that direction of force and displacement as same. But if they are not in same direction, the graph must be plotted between F cos theta and R, where R will be displacement and F cos theta is the displacement. F cos theta will be the component force along the displacement. Work is a scalar quantity. As I have explained earlier, dimensions of work can be obtained from the product of force and displacement, and that comes to be ml2 t minus 2. The unit of work will be either mks or cgs. The absolute unit will be joule and erg. Joule is mks and erg is cgs, and 1 joule is 10 to the power 7 ergs. Gravitational unit will be kilogram meter and CGS system will be gram centimeters. 1 kilogram meter is 9.8 joules or 10 to the power 5 gram centimeters. Now our question is that force displacement diagram shown in adjoining diagram, the work done by force in displacing the body from x is equal to 1 to x is equal to 5, that is shown in the figure. So it is clear in the figure, the force is taken on y-axis, displacement on x-axis, and the line will be strong where the work is done. The work is area under the curve and displacement axis, and that is according to the figure will be 10 plus 20 minus 20 plus 10. Means that is we are finding 10 plus 20, and that will be minus 20 plus 10. So we add the two numbers, subtract 20, and finally we get 20 ergs.